Hello boys and girls, welcome to another episode on our YouTube channel. My name is Craig, I'll be your host in this vlog where I discuss beer and do something with electronics. Today we've got something rather special on the bench. We have a grid tie inverter. So I'm not going to waste any time. You know the issues we're having with our power provider in South Africa. Let's jump straight to the bench. I've got a simplified schematic of what this thing is and what it should do. We'll go through the simplified schematic and then we'll have a look inside this thing and see what we find. Catch you on the bench. Right, so here on the bench we have our grid tie inverter. This happens to be a 3-phase 400 volt AC output to the main grid. It also happens to be a transformerless grid tie inverter, and we'll see very shortly from the circuit diagram why this is a very, very dangerous idea. The input on this thing, power, I think is 8.5 kilowatt, that's 8,500 watts, and it's up to 1,000 volt DC of PV cells. So already this should ring alarm bells with you. There's a few safety precautions we have to take with this. This is not for the hobbyist. This is not kids play. This will kill you. Our circuit diagram, let me just zoom in a little bit and we can explain this. Our circuit diagram for a typical grid tie inverter is pretty simple. If I go around this side, we have a DC in bus, capacitor, inductor for filtering. You may notice this circuit from before. If we put a FET here and a diode over here, we've in fact created a boost circuit. Remember, this is just a typical diagram I've taken. So normally we would create a boost circuit if we're using one solar panel, which might be say 50 volts or whatever we need to get this voltage up. You'll notice that there, on the output of our diode, we complete our boost circuit with our filtering capacitor or our bulk storage capacitor. Then we have this configuration of 4 field effect transistors up here. I haven't drawn in the control circuit, but this would normally be pulse width modulation to control our power and our voltage. Then we'd have a step-up transformer because we need to bring this 50 volts up. Remember, our mains voltage in this case is going to be running at 400 volt AC 3-phase. That means the 3 phases are out of phase from each other by 120 degrees. So we'd have our step-up transformer. We'd rectify that back to DC. We'd have some filtering again. That would give us our DC bus. Then we would invert our stepped up DC bus with this H-bridge configuration up here. So what we'd be having is that. Then we have a common mode choke with a capacitor. That is to filter out those harmonics to give us a sine wave. So if we filtered that, remember how our inductors and our capacitors work, we would actually get a nice sine wave. We have another inductor, and we have to have a switch to isolate us from the mains in case something goes wrong. These systems are not allowed to act in island mode. What that means is if you lose your IPP or your power provider, this thing must isolate itself from the grid. Very simply, if it doesn't and the grid comes back, well, you'll blow this thing up because this is nowhere near enough power to compete with your power provider. So I've just drawn it as a switch, but it would be a very fast acting switch, a solid state switch, and then would go into our grid. Well, in this case this is very simplified, but we have 3-phase AC out. So I'm going to keep the schematic at hand. What I want you to remember, this is big power that we're playing with in here, and the precautions that I've taken on the DC input side, you can't see it's on there. I've actually shorted out the positive and negative, well, the positive to the negative of each input bus. It's got 2 input buses, and I've shorted that to ground. Simply put, you will see in this design we don't have any of that. Our DC is actually coming in here with a little bit of filtering and whatever because of the pulse width modulation. Now, you don't want that going back to your PV cells. So our DC, to all effects, we have capacitors and chokes across here, and then we inverting it and going out to three-phase mains. A transformerless design, although it is legal, it's allowed, there are precautions you need to take around it. The problem with that is if for whatever reason you don't have this, typically on your PV cells, if you think of it, if you synchronize, that switch is closed, you could have power provider potential on your PV cells because you don't have this isolation. The second problem, without having this isolation, normally we would earth one of these buses, and that would typically be the negative. Now you can't earth any of those buses, so you start seeing where the hazards come in. If you can't earth it, you are now floating, and it becomes quite a safety risk. So let me open the box up and we'll have a look inside and we'll compare it to our circuit diagram. Right, so we have the cover removed of our grid tie inverter. What you can see down here, here's our on off switch, here's our DC input. It comes into this board. We have some protection, transient protection here. You have a controller board on top, so we can't really see. We need to remove this controller board because I don't believe the problem lies here. It's going to lie down here. Apparently this thing is very dead. You have a nice controller board up here, and this controller board is what is going to control all the pulse width modulation, wave shaping and everything like that. So I can't really explain underneath here. All you can see is there's a nice big choke under here. Will come through. There's another little board down here that we'll see better when we take this off, and here we start having capacitances. This is the AC side of the board. In other words, this side, it's already been inverted. You can see these big capacitors that we have here, more capacitors and resistors, chokes. We can see 1, 2, 3 different phases. So we've already inverted it, we converted, and what they're doing here is they're taking that AC, that pulse width modulation wave that we talked about up here, and they're shaping it to that with all this capacitance and inductance. Then we go out with our 3 phases up here, and interestingly enough, they're giving you a neutral. What I don't see is, I don't see in here anywhere where this chassis, the chassis itself is earthed. Maybe up there, I do see an earth wire. Up underneath there, the chassis is actually earthed. So they do earth the chassis, so that's a good thing. But remember, this is a transformerless design, so if we go back through all of this, your AC is typically flowing back through the coils, back through here. You are sitting at, potentially you could be sitting at AC potential up here. What I do see, these little relays up here, those are to switch off and isolate you in case of an islanding situation. So whatever sensing they're picking up, hang on, I don't have ESCOM, or I've lost whatever a phase, these will open you from the main grid. So what I'm going to do, I see they've cable strapped these ribbon cables on, so they've learned their lesson the hard way. They've picked up before that you can have vibration and noise in these things, and these ribbon cables actually pop out. So they've actually had this issue before, so they've cable strapped them down. So what I'm going to do, I'm just going to take out 1, 2, 3, 4 little screws, so we can have a look. Why is there a little bit of copper wire there. Huh? Anyway, I don't believe the problem lies up here. I don't believe it lies on this control board, but we can soon find out. We'll lift this board, and underneath here what we hope to see is some protection and relays and stuff, and the H-bridge control circuit for this. So let me remove this board, and then we can take it further and look at that circuit in detail. Funny thing, I've just started taking out, you can see I've taken out that screw there, and I've taken the one out on this side. What I'm seeing, can you see that over there, that little copper piece of wire? And there's another one here. Now, why would I have copper strands sitting on this board? That makes me very, very worried. Anyway, let me finish removing this board, and then we'll take a look underneath. Right, I've removed the control board. It's just mounted on one of these, so you have to remove these. It's there for shielding and isolation. What we can see is our PV cells coming here. There's one, there's the negative for the 2-volt PV cell, and here's one, and its negative is down here. We come through some rather large inductor, toroid, filtering capacitors, more filtering capacitors, more inductors. Interestingly enough, under here we can see 1, 2, 3, 4, our 4 IGBTs or MOSFETs, whatever they're using, probably IGBTs, to make up the H-bridge. What is interesting enough is there is 2 per bank. In other words, they have paralleled them because of the current. So that'll be our switching. Will come out filtering. Again, remember, this is going to be our PWM sign, and then we'll go up to our AC, the AC side already, and do some filtering. What is interesting, I see a whole bunch of little MOVs down here. For transient suppression, there's also little gas discharge diodes in there. There's one. There's one. These are little relays down there. What I don't see is I don't see any fusing on this. So I'm rather curious if, am I blind? These little yellow MOVs, GDTs, relays. Yes, I really don't see any fusing on this. Let me I'm just going to move the camera out the way, and I'm just going to have a closer look, and I just want to confirm that there's no fuse protection on this. So I'll be right back. So boys and girls, while I've been looking for protection on this board, it seems as I've been talking out of my bum to you. If you've taken a quick look up there, we've got a positive and a negative. We've got a positive and a negative down here. We've got 2 streams, 2 PV cell streams. What I thought was the H-bridge circuits down here are not H-bridge circuits down here. All these 2 streams do is take the 2 DC streams, do whatever protection through the MOVs and and filtering through the common mode choke capacitors, some more filtering through inductors. The two streams come together. I don't know what is under there, but there's some resin filled bay. It comes back. We go through these two capacitors, and we end up on this DC bus. So what I've done, I've just gang chained my power supply. In other words, I put the two channels in series. Put this here, and I measure from ground. Notice I'm measuring with one hand. I'm going to measure ground to the positive DC bus. We're getting 48 volts, which is what I'm putting in. So this board under here is nothing, there's nothing wrong with it. And this processor board is not doing what I thought it was doing. It's not doing the switching or anything. From this board here, it goes underneath to this board. This is our actual inverter board here. That does the inverting, brings back the three-phase AC up to here. So what I'm going to do, this processor board obviously does comms. It measures certain points on this board with its current and voltages and whatever, and it will bring it back to this processor, which I think handles the comms mainly for this LCD display and its inputs and all that sort of logic and stuff that goes on there. So I'm going to put back the base plate for here, and then what I'm going to do is I'm going to take out this board here, or I'm going to lift it out so we can actually see what's going on this board, because I think our fault lies on that board. What you can't see, well, maybe down there, coming out of that, underneath there's a little NTC, so we have NTC protection in this board as well for over temperature. So obviously it's measuring the temperature of these heat sinks. These are transistors, these two bridges, transistors in parallel. Then what we do is we come through blocking diodes. So whatever's happening in whichever bus cannot push back into the other bus, and whatever's going on there shouldn't be able to push back into this bus, and that's what that's there for. So let me put this board back and connect it up, and we'll take the AC filter board out and have a look at what's going on underneath here. Right, boys and girls, it looks like I've been talking up my bum again. I've had a look under this main board up here, and there's nothing really there. There's a bunch of FET drivers, field effective transistor. Again, this is the filtering, and this still remains the control board. I actually had a look at this Texas Instruments chip data sheet, and it's designed specifically for this type of thing. It's got all your sine, cos tables and everything built in, so it is built for this, and it's got multiple pulse width modulation outputs and everything. There is no ways I can power this circuit from my bench power supply, which we've seen in previous videos. My bench power supply, if I gang chain it, putting the two channels in series, I will only get 60 volts out. This circuit needs a minimum of 300 volt DC to power it. So I'm going to do something. I do not recommend you do this at home. I know what I'm doing, and I know the risks associated with it. I don't have a variac, a variable transformer or auto transformer at home, so what I've done is I've built a little circuit. I can show you here on the side. It's just a rectifier with a little bulk storage capacitor. So in other words, if you don't know what I'm talking about now, then you definitely shouldn't be doing this. If I took 230 volt AC from the mains, I rectified it, I will get 325 volts, and if I smooth it out, I should have roughly about 325 to 329 volts DC RMS. That should be enough to power this. Please, if you don't understand what I've just said, you shouldn't be playing here. There are no short circuits on this board. I've measured that out. I've measured the input for short circuits. I've measured the outputs for short circuits. I don't get any short circuits. What I'm hoping to achieve is that we can power this board, because with a 60 volt DC, obviously it's not enough to bring in the circuit below here. It doesn't sense that it has enough voltage. It won't switch on. So I'm really hoping to switch this thing on. We cannot tie this back to the grid, obviously, because I don't have any three-phase outlet in my house or anything like that, and so I'm not expecting these relays to kick in. What I'm expecting is hopefully not a big bang. I'm expecting this thing to operate in island mode, because I don't find any fault on the board. And what I'm suspecting, the big problem with this is, because it's a transformerless design, in other words, you've seen, we measured the DC voltage when we put in a little bit of DC voltage all the way through. You cannot earth this side of it, and I'm suspecting that this is what the client did, is they actually earthed it. This thing says, it has a fault, bugger you, I'm not even going to switch on because it's dangerous. And that's what I'm suspecting. The problem is you're getting three phases, a neutral and an earth, a 5-wire system from the grid in South Africa at 400 volts or 400 volt AC, 380, whatever you want to call it. The problem with the 5-wire system is your utility will provide the earth, not you. You cannot, because it's not isolated. So I'm going to take a lot of precaution when I do this. I'm going to put on, first of all, I'm going to be wearing, a flash jacket, and I'm going to be wearing gloves when I switch it on. The flash jacket is rated. I'm not going to go into explaining that too much. Just know if you're switching voltage and things like that, you would need to wear something like that. So I'm going to take precautions. I'm going to wear a flash jacket, and I'm going to wear gloves, and. So what I'm going to do is, I'm going to just get kitted up. Of course, I'm also wearing insulated boots, so I'm insulated from the floor. So typically I'm completely insulated. I'm just going to get kitted up, and then we'll come back and we'll switch this on, and we'll see if it, I'll leave you guys to see if it flashes or whatever, but I will be obviously below this. My head will be below this. I'm plugging it into mains unit that is running through a RCD, or earth leakage residual current device. Earth leakage is in South Africa, so I'm not too worried about that. Like I said before, this is very dangerous. If you don't know what you're doing, don't do this at home. Ideally you would want to do this through a auto transformer or something like that, so you could bring the AC mains up slowly. So let me get kitted up. We'll come back and we'll switch it on. We'll see what happens. Okay, we're back. As you can see, I'm wearing gloves, flash jacket, and everything else like that. I don't have rubber gloves at home, unfortunately, so I don't carry substation switching gear at home. Well, here we are. Let me switch it on. I'm going to go below this, and there we go, on. And good lord, it switches on. On the LCD I'm reading 332.3 volt in on our DC bank 1. So our rectifier circuit works. Again, I don't think anything's wrong with this board. I think these oaks have tried to earth one side of the DC bus, which you can't do. What we can do, I'm just going to set it up for this, we can measure some voltages on that side of the of the board we've got 3 phases and a neutral, and then there in the middle we have a bunch of isolation relays. If I measure AC voltage here phase to phase and phase to neutral, if I get phase to neutral of 230 volts around there and phase to phase voltage of 300 volts, then I know the inverter side of the board is working, and I can be pretty sure that whatever logic is happening in this chip down here is keeping those relays in, because we are, or keeping them out, de-energized, because we are in island mode. So let me get the shot set up, and then we'll come back, we'll take a few readings, and if those readings are healthy, then I don't think there's anything wrong with this inverter other than user error, which is always a problem. But it powers up, so our little design works. So it's gone into screensaver mode there. So our design works. I'm actually very, very chuffed. Like I said before, if you don't understand how I got to 325 volts from AC mains by rectifying it, then please, that's very basic. You shouldn't be playing in here. I'm still going to keep the flash jacket and gloves on while I take measurements, obviously, because this is not it's not the nicest of things to be working in, and I can't do one-hand measurements because I'm just slack. So what I'm going to see, if I've got another little clamp for my meter, we'll hook it up and we'll take it from there. So let me get the shot set up and we'll come back. So boys and girls, I've actually been very dumb today. I don't know, I must be getting ill or something. We are not going to get voltage here because our inverter doesn't sense mains. So if I look at the LCD screen, it tells me I've got 330 volts DC coming in from our little circuit that we've made. On the inverter side, we've got basically 1 volt out. So that's its little sensing, but at 50 hertz. One thing I did go into is I went into the events list, and basically it tells me no utility. So this thing is not going to do anything in the state it is. I've set the date right and whatever. I do believe that this inverter is right. I don't think there's anything wrong with it. I suspect, again, either they earthed the negative with the positive of the DC bank, which you can't do with this inverter, or the inverter overheated underneath this, as we saw earlier on, underneath these boards where the little transistors are mounted and whatever, we have an NTC resistor, a negative temperature coefficient resistor, and that's there for temperature protection. So what I suspect, either it could be an installation problem, like I said, they've earthed a negative, which they can't do, or I suspect that this thing overheated, and I suspect it could have happened recently because we are in summer in South Africa and we've had an exceptionally hot summer this year, and so I suspect this thing overheated, shut down to protect itself, and these guys thought it had failed. Ideally, what you would do when you mount this thing is build a bit of a glare canopy, sunshine protection canopy around it so that it doesn't overheat, but that's what I suspect could have happened. I really don't find any faulty components on it. I've been through the main components. There's nothing much to this. There's nothing that can really fail in it. If we look at it, I don't really want to go poking around in here with a metal object, but let me see this will work. If you look at it underneath here, we've got our DC bus coming in. We've looked under this board. We've got a common mode choke. We got a whole bunch of filtering because this thing is switch mode, so we don't want it going back into our PV bank. More filtering. The DC bus goes into the bottom. There's a bunch of optocouplers below this board that are switching our FETs. It's all controlled by this board, by that chip there, that controller. That'll switch, bring back our three-phase AC with a neutral. We now take that pulse width modulation, those three phases, and through RC banks, well, in this case LC banks, inductor capacitor banks, we take that pulse width modulation and make it into a sine wave. We have relays to cut us off from the grid, and this circuitry up here is really just to sense the power provider side, phase and phase angle and all those sort of things, so that we can get this circuit into the same phase angle as the mains, obviously, and the same voltage, amplitude, and that sort of stuff, and then push our current back in. So there's really nothing much here. The inverter tells me that it's fine. The only thing that I've done is I've turned down the contrast on the LCD. I do believe this is right. I actually am suspecting that either it's an installation problem, which I don't believe, because I went into this thing and it's got 9,000 plus operating hours, so I don't believe it's that. I just think the South African sun got the best of it. Again, I want to stress, this is not play electronics. This is power electronics. If you don't know what you're doing here, you shouldn't open this. And if you don't know how I got to this to power it up, it's really not for me to give you a lesson on that. Rather just stay away. Either way, I think it was interesting. We had a nice look into it. Interesting enough, the red LED flashing tells us that it's a recoverable fault according to the product manual. There's not much that you find in the manuals on this thing. It's very dear macabre. It's not exactly nice. The minimum input voltage, DC voltage, to power this thing, 300 volts. So we took our 230 volt AC mains, multiplied by the square root of 2. You see where I'm getting the DC RMS. Default password for this thing, very difficult to find. Apparently 0001111. That's 00011 on the default password. For me, this one was all ones, so 6 by 1. If you come across this thing and you're trying to get into the menus or whatever, maybe that helps you. Funny enough, the protection on this thing is very strange. There's no fusing, there's nothing like that. What they do have, a lot of MOVs, and in the bottom there you probably can't see it very well, gas discharge tubes, which is a funny thing I haven't seen in a long time. So what they've done is they've connected the gas discharge tube in series with the MOV. So the gas discharge tube will open first, obviously at a lower voltage, lower transient voltage, and the bigger brother, the MOV, will open as the voltage increases. When we say open, I actually mean close the circuit to ground to pass the transient. All in all, I don't think it's a badly made board. Neatly laid out. They seem to have done what they need to. I just don't like this type of design. I don't like a transformerless design where we don't have isolation, but I suspect due to the power ratio of this device, that you are not going to get many transformer designs. suspect they would be switching in quite a high frequency up here in the couple of hundreds of kilohertz up to maybe a couple of megahertz. And that brings the component sizes down and obviously the cost, so that's why I suspect you're not going to find a transformer design. So I'm going to wrap it up here. I'm going to call it a success. I don't really know what to tell you. Sometimes we just get lucky and we have user error. So let's wrap up the design, or let's wrap up the video and close it out. Alright, boys and girls, here we are at the end of another video. Finally I can have a beer. I'm just drinking a line. I don't really like to mess around with power electronics and have a beer. I'm sorry that there wasn't any major catastrophic fault in the device. Sometimes we just get lucky, like I say. I suspect the summer sun really got the better of this thing. I can't see it being installation fault. Not with 9,000 plus hours of running time, so I suspect the thing overheated, shut down and said sorry, and they looked at this and after maybe whatever time that this thing was standing in the sun said okay, it's failed. As always, be careful when you're playing with power electronics. There's huge voltage in there and huge amperage. There's nothing to stop it from doing you in. There is no, in a field installation like this, there's no earth leakage or residual current device that's going to save you. Also be aware, because it's a transformerless design, that you potentially have your power provider mains at your PV cell, and that's quite a dangerous thing. Anyway, as always, I hope you had fun. I hope you learned something. Take care until the next time. Cheers.